Alright, so hello everyone. This is gonna be the second online recitation that we're having, and today we are gonna be doing conservation of angular momentum. So let's write that down. There we go. Alright, so we're gonna be doing three problems, and then I will assign you to do one problem for this week. And we're gonna start doing this first problem. So the 150 pounds car of an amusement park ride is connected to a rotating telescopic boom. When R, the radius of this arm right here, that distance, that's gonna be changing. So when R is equal to 15 feet, the car is moving on a horizontal circular path with a speed of 30 feet per second. If the boom is shortened at a rate of 3 feet per second, determine the speed of the car when r equals 10 feet. Also, find the work done by the axial force F along the boom. Neglect the size of the car and the mass of the boom. Alright, so let's see. Okay, so we need to find if the boom is shortened at a rate, determine the speed of the car when r is equal to 10 feet, right? So we need to find that, but we also need to find the work done by the force along the boom. Okay, so we're gonna do here, we're gonna actually just gonna use this figure to draw my velocities. So for the initial state, state 1, we are gonna have a velocity v1. It's gonna go like this. It's gonna be v1, okay? And then we are gonna have second state, and here is gonna be the DAG. There we go. And at this state, we are gonna have two velocities, okay? We are gonna have the tangential velocity v2 and this velocity right here of the boom getting shorter, and that's given 3 feet per second. So we're gonna call this velocity v2 r, and that's equal to 3 feet per second. And this one right here is gonna be v2 theta. There we go. So we're gonna have those two velocities. I'm just gonna change my color here. Try to, okay. So there we go, that's better. It's gonna be my v2r. So you can tell that the total velocity, take the green, just gonna be that component right there, the sum of those two velocities. Okay, so to solve for this, we're gonna use conservation of angular momentum. So we're gonna start writing the conservation of angular momentum equation, where we have this 1 and 2, which indicate the initial and final state, and here this notation right here, it's indicating that that's gonna be the angular momentum respect the center O. Alright, so let's write the equations down and see what we got. So we got the initial position times the mass times the velocity at 1 equal r2 times m times v2 and theta. And this is really important right here, because as you can see, I'm taking this velocity right there, the one that is tangential to the path. Okay, that's the one that is creating angular momentum, because as you can see, is the one that is perpendicular to the arm, which is also the moment arm of the problem at state 2. Alright, so let's go ahead, let's solve for this. You can tell that the mass is gonna cancel out, so we can have v2 theta equal r1 times v1 divided by r2, and that's gonna be equal to 15 feet. Again, I just want to keep my units all the way through the problem at every single step, divided by 10 feet, and then the velocity right here, v1, that's given, and I believe that's 30 feet per second. Okay, there we go. So if we solve, v2 theta is equal to 45 feet per second. That's the first part of the problem. The second part is to calculate the work generated by the force of that arm. So to do that, we are going to use the principle of work and energy. And that kind of makes sense because we can relate energy and work, so we can actually get that number. So we write that equation down, it's going to be T1 plus summatory of all of the forces done through the process equal to T2, where T1 and T2 is equal to the kinetic energy. So we can write that again. The only force is going to be the force done by the arm, and equal to the final kinetic energy. Alright, good. Now, let's start solving for the first term. The velocity, what's the mass? The mass is gonna be 150, and that's pounds divided by 32.2 feet per second square, correct? Then divided by 30 feet per second, and the entire thing square, plus UF, that's what we need to solve, equal 1/2 mass, which we already know it's gonna be 150 pounds, divided by 32.2 feet per second square, times V2. So a lot of people will go ahead and write the V2 theta the one that is tangential. But that's not the only component that is creating kinetic energy at the state 2. V2, and I'm gonna make a parenthesis right here, V2 is gonna be equal to the square root of V2R squared plus V2 theta. And that's the velocity that we need to use to calculate that kinetic energy. So that's gonna be 45. We got that number, and I will go ahead and use my units again. Plus, it's gonna be 45 squared plus 3 feet per second, the entire thing square. We saw for that we're gonna have 45.1. Pretty close to 45, just because the normal component of the velocity of the shortening rate is very small, but this is the velocity that we need to use to calculate that kinetic energy. Awesome. Now I'm good to go. We can go ahead, solve for UF, and that's gonna be equal to 2,641 pounds per feet. And that's the second part of my problem. Alright, so takeaways from this problem, it's like we always need to consider how my velocity vectors are going, and we always need to use the tangential component of that velocity for my conservation of angular momentum equation. And if we want to calculate kinetic energy, we need to use the total magnitude of the velocity. Okay, let's go ahead and solve this problem right here. An Earth satellite of mass 700 kilograms is launched into a free flight trajectory about the Earth with an initial speed of VA equal 10 kilometers per second. When the distance from the center of the Earth is RA equal 15 megameters. If the launch angle at this position is 70 degrees, determine the speed VB of the satellite and its closest distance RB from the center of the Earth. The Earth has a mass of 5.976 times 10 to the 24th kilogram, and we are given a hint. Under this gravitational force, F equal G MEMS over R squared. Okay, well, let's go ahead and solve. Let's see. We need to calculate the velocity. So here, this is kind of nice because in the problem is the diagram with the velocities are already given, and we need to solve VB and RB. Okay, so we're gonna start using conservation of angular momentum. All right, so the center of the Earth is gonna be point O, and with that notation, we're just gonna go ahead and write the conservation of angular momentum. All right, so we're gonna have R1 times mass times V1 equal R2 times M mass times V2 theta. Again, for this position, I'm sorry, I think I'm just gonna go ahead and rewrite that equation. Let's see, okay, let's do it again. Okay, it's gonna be ms, mass of the satellite. Then we're gonna have VA, but we need to calculate that component right there. So it's gonna be VA sine of VA times RA. And that's gonna be equal to the mass of the satellite times VB times RB. Alright, first equation, it's right there. Let's go ahead and substitute everything that we know from the problem. So we're gonna have 500 kilograms, good, times, we're given VA, and that's 10 kilometers per second. We need to convert that to meters per second. That's gonna be my conversion. Then kilometer with kilometers cancel out, and I'm gonna have meters per second. And then we need to multiply that by sine of 70 degrees, right? And then we need to multiply by the distance, RA. That's gonna be 15 megameters. So we need to convert that to meters, where a megameter is a million of meters. Okay, that's happening again. We'll cancel out those units. Okay, and then that's gonna be equal to 700 kilograms. Okay, in fact, you can tell that this and this can cancel out. Then we're gonna have VB RB. Okay, I'm gonna go ahead and solve for some. So let me make sure. I'm gonna solve for this, and I guess that's what I'm going to do. Just need to do some quick calculation right here, so bear with me. There we go. Alright, so I'm going to have 1.4 0.95 times 10 to the 11th, and the units for that is gonna be meters square per second, because basically it's gonna be velocity times position. So this is my first equation, and the equation that I got from my conservation of angular momentum. Alright, so you can see we have one equation, we have two unknowns. So we need one more equation. Excuse me. So let's see what else can we do. In the problem, it's given this hint right here, so we're gonna follow that advice. So we're gonna apply conservation of energy. There we go. So we're gonna have kinetic energy plus potential energy equal kinetic energy at the state B plus potential energy at the state B. The kinetic energy is just gonna be 1/2 times mass of the satellite multiplied by VA, and that term is gonna be square, plus that potential energy. And here we need to use the gravitational equation, gravitational force. Okay, but remember, I know that my kinetic energy, the units are joules. Okay, so here what I'm given is force that I'm gonna call F. Okay, I'm gonna call it Fg just to make sure I'm talking about the gravitational force, and I need to multiply this gravitational force by R. For this case, Ra. Then we're gonna keep solving. Alright, let's go ahead. So I said like my kinetic energy is equal to joules because that's energy, and my potential energy is also equal to joules, and I can check this out. So newtons times meters, that's joules. Okay, that makes sense. And I go ahead, keep solving for this. It's gonna write the kinetic energy as it is, and now I'm just gonna substitute by the gravitational force. So that's gonna be G, the gravitational constant, times M E M sub E and M sub S divided by R A square and multiplied by R A. So you can see that this is gonna cancel out. We're gonna go ahead and solve for. So I just noticed right here that I was missing my second term of potential energy. So similar, my RB, one term, is gonna cancel out. Alright, okay. Now let's go ahead and try to solve for this equation. So we're gonna have 1/2 700 kilograms multiplied by VA. So it's gonna be 10 kilometers per second. So 10 kilometers per second, and again I need to multiply this by 1,000. I just wanna make sure that my units are working out, otherwise we'll get a wrong answer and we don't want that. Okay, I think that's fine. Then we're gonna have my G constant, which is 66.73 times 10 to the minus 12, and the units for that are gonna be meters, cubic meters divided by kilogram second square. Alright, mass of the earth, that's given in the problem. It's gonna be such a long equation. Okay, it's gonna be 5.9 7.6 times 10 to the 24th and multiplied by the 700 kilograms. So this is kilogram, this is kilogram, okay, of the satellite. And then we need to divide by 1 time RA. So that's gonna be 15 times 10 to the 6th meters. So that's half of the equation. Let's go ahead and solve for the other half. So we're gonna have, at this point, I'm not gonna write the unit, but I don't know, should I? No, I'm just gonna, but I mean, it's just gonna follow the same units as the first part of the equation, the first term. Okay, so we're gonna have 1/2 times 700 multiplied by v squared. We don't know that. That's what we're trying to find. Plus, it's gonna be, actually it's gonna be minus, and this carry here is also minus right there. So yeah, the gravitational energy is gonna be negative all the way through the problem. So sorry about that. So there we go. So we're gonna have minus. We write as the gravitational constant multiplied by 5.976 times 10 to the 24th times 700. The entire thing divided by RB. Okay, so we need to find this, okay? So I'm just gonna make this equation a little bit nicer. Gonna solve for some of these terms. So we're gonna have, let me use the calculator again. Alright, so we're gonna have 1.639 times 10 to the 10th. No, that's not right. Need to. Alright, let me rewrite that. That's gonna be 3.5 times 10 to the 10th. Okay, that's good. Equal 1/2 700 VB square minus 2.79 times 10 to the 17th divided by RB. Okay, now we got to this point. We have this equation, and we also have this equation that we got from here. So we got two equations, two unknowns. We can go ahead and solve for VB, which is 2 kilometers per second, and RB, which is 13.8 megameters. There we go. Alright. Second problem is done. Okay. Let's go for the last problem. So A 4-pound ball B is traveling around in a circle of radius r1 equal 3 feet with a speed of vb1 equals 6 feet per second. If the attached cord is pulled down through the hole with a constant speed of Vr equal 2 feet per second, determine how much time is required for the ball to reach a speed of 12 feet per second. How far R2 is the ball from the hole when this occurs? Neglect friction and the size of the ball. Okay. So let's see. We're gonna start the problem calculating the v theta. Let's see what is that. So let's see. Here we have this. Actually, let me try to this velocity right here. I'm gonna draw it right there. Okay. And then we also have this velocity right here, which is gonna be actually, let me use different colors. Okay, so this one, that one, and then in this color we got this one right here, which is this one right there. Okay. All right. So just give me a second. I think I need to double check. All right. So okay. Okay, so let's see. I'm gonna redo this drawing, but now I'm gonna be looking from the top. Okay, so we have the ball right here. Okay, so what I'm gonna do first, I'm gonna solve for V2. So this is gonna be my state 1, and then this is gonna go to somewhere here where sure it's gonna be state 2. There we go. Okay, so now let's kinda okay, trying to make this straight. Okay, that's a little bit better. Okay, so for VB1, the velocity at the initial state, we are going to have this velocity right here. And that's given. That's gonna be V1, I'm just gonna call it VB1, and that's given. Okay, now for state 2, it's gonna be, we're gonna have this velocity, which is Vr equal 2 feet per second, and the total velocity goes like something like that, because we still need to calculate this velocity right here. So this total velocity, is VB2 equal to 12 feet per second. Okay, and this velocity right here, I'm gonna make it, it's gonna be V theta 2, and V1 is given in the problem is 6 feet per second. There we go. Okay, so my analysis is done. Let's go ahead and solve using conservation of angular momentum. So this is gonna be the center, 0.0. So if we want to solve for this, we're gonna have 4 pounds divided by 32.2 feet per second square. There we go. Equal, no, times velocity. This velocity is gonna be the 6 feet per second times r, which is 3. There we go. And that's gonna be equal to same mass, right? The mass is not changing from state 1 to state 2, multiplied by this velocity that we need to calculate, and multiplied by r2, and we don't know that. Alright, so this right here is gonna be my conservation of momentum. And again, I'm gonna cancel out the mass because just constant. Okay, so I can calculate V theta 2. I can do that because we know that the velocity state 2 is equal to the square root of VR square plus V theta square. So if we solve for V theta, two, because we know that this is 12 feet per second and this is 2 feet per second, we get V theta 2 equal to 11.83 feet per second. Alright, now I can solve for I can solve for R2 since I have V theta 2. So if we do that, we can have R2 equal to 1.52 feet. And if we want to calculate the time that it takes, we just need to take the increment or the change in the position of R, so how much is the displacement in the R direction, and divide that by VR, which is constant. That's why we can do this. So now R goes from 3 to 1.52, and that's the increment that we need to use, and we divide that by 2 feet per second. That's equal to 0.739 seconds. And that's it.